I'm going to be presenting about a dietary exposure tool, screening tool that was developed by Exponent and my colleagues at Exponent, Natran, Karen Crawford, and Terry Troxel. And we developed this tool at the demand of ILSI, basically at the demand of food industry, who really needed some tool to help them prioritize when they see a contaminant, when they see one of those metals. You know, you just heard about all these metals that could be found in the diet. So when they see a metal in an ingredient or in one of their products, they needed to know, is this something we need to worry about or not? So we developed this tool for this particular purpose. You heard about metals. I guess I'm going to be repeating what Dr. Ortiz just said. So basically, it's fine. Metals are found in the soil, water, air, etc. There are multiple sources. And they've always been in the diet. We've always had some arsenic in our diet. We've always had some lead in our diet, some mercury in our diet. So there's always a metal in our diet. And it's, you heard about the total diet study, and I apologize, I had no idea that FSIS was sampling for, and looking for metals too. I should have done my homework better. So I could have listed here that also FSIS has found metals in meats and poultry. But looking at the US total diet study, you see it. You see that we have several metals that have been detected. You saw the entire list of metals that are tested. You can see metals mentioned in CFR citations, setting up limits for levels. You can see that in the Food Chemical Codex specification, setting up limits on how much lead or arsenic could be in food. And also JECFA, which is the Joint FAO-WHO Expert Committee on Foods, also has set limits for both arsenic and mercury and other products. So, as I mentioned, because metals are found almost everywhere, and the analytical tool, the chemical tools are getting better and better, so we can now detect them at even lower and lower levels. So now when we find something, do we need to worry about what we're finding? So we're finding them more often. But also there's something to remember, that some of these metals are also beneficial for us. So basically, typically, when we're looking at the metals, we have this U-shaped curve, which is at low doses, we really need them, and maybe at higher doses, they will become toxic. And there are the guidance levels also are being lowered. The tolerable dietary intakes are lowered lower and lower now after review of the toxicology and because now we're detecting them more often. So industry has this issue to say when a food company or the quality assurance person in a food company finds something or is told that, oh, we found something in a sample, in our data, in our product, they have to worry about, is this something we need to worry about or not? So we were asked to develop what we call the metal dietary screening tool, short MDEST. It's a screening tool that allows the quality assurance person or a food industry person to basically figure out what that levels that was detected, plop it in the model, and quickly estimate the exposure that you'll get, that you could be getting it. It is using consumption data from the NHANES survey. NHANES is for those of you who are not familiar with it, is a food consumption survey that is a continuous survey that is conducted by CDC. It has a food consumption pattern called the What We Eat in America component, and it basically collects information about everything that somebody has consumed over 2 non-consecutive days. It asks about 5,000 people per year, so every cycle of NHANES is typically 2 years. For over those 2 years, it collects data on about 10,000 people that tells us what they have consumed over 24 hours, over 2 dietary. So it's a very, very rich database of what people eat in the US. And So we use consumption data from that survey, and we look at what are the limits that are out there that are available. For instance, how much, what's the maximum limit that's allowed of lead in water? What's the maximum limit that people can consume of a certain chemical, of the lead, arsenic, cadmium? What are the maximum values that people could consume before, that have been set by regulatory agencies? And we use these limits to basically say, okay, this is a worst case scenario, this is a maximum you could consume, what's available out there, how much is available in the diet? We take that part out of this limit and say, okay, that's how much now is available. We use that fraction and apportion it to the various foods to basically use in our model. And it's very abstract. When we go through it, you'll see how this is done on a compound by compound. Most of you are probably familiar with the risk-based approach. The MDEST uses basically the traditional use-based approach. In our first module, we looked at the hazard characterization, which basically looking at what are the default exposure limits that are available out there, what's the total exposure that's out there, how much do we allow for the tool. So the MDEST includes default values, but the user can override these if they have better data, basically. Then it has the second module, which is a dietary exposure module, where basically you can go in and put in the concentration and estimate what is the exposure. Then as a third step, it says, okay, if that's the exposure, what is the risk from that exposure? And it develops so that will be your risk characterization. 5 compounds are set up in the model: arsenic, cadmium, chromium, lead, and mercury. But because these, as I said, the limits can be overridden by the user, I can see a user basically taking it and putting it in their own, the data for selenium or the data for molybdenum or whatever, and then run the assessment the same way. This is a schematic about how the product works. I don't know whether I can use, you don't want me working with a laser. I would get you dizzy. I'm not very good with lasers. I make you dizzy. Yeah, let's not do that. No, let's not do this. Okay. So basically, as a first step, you figure out what is your compound. So what is the compound? Do you want to use the default value, or do you want to use your own values? Then it goes to saying, okay, what consumption data do you need to use? And the consumption data are important because it depends on where that food was, where that compound was detected. Was it detected in a finished product? Was it detected in a raw agricultural commodity? So you go through that process to decide which consumption data do I want to use. Then you plop in your value, and then it estimates the exposure and gives you the risk assessment. So I'm going to go through the default values that we use in MDEST, and just to give you an idea about how we arrived at those limits. But again, if more recent data are available, the tool can be updated because these can be changed manually. For arsenic, the FDA has set a limit of 10 parts per billion of arsenic per liter of water. So assuming somebody consumes 2 liters of water, we estimated that at most we could be exposed to 0.3 microgram per kilogram body per weight before we exceed whatever limit FDA had in mind when they set that limit. So we looked at the data on lead and to estimate the potential exposure from the background, how much lead do we get through the diet. And we ended up saying, when we evaluated the exposure, we were sort of exceeding the limits because the data were very conservative, the data that we had. So we ended up saying, if the tolerable daily intake is 0.3 microgram per kilogram per day, we're not going to allow you, for your particular case, for that particular screening product, when you find it in one food, we're not going to allow you to basically go all the way to 0.3 microgram per kilogram per day. We're going to say that the background has to have a certain fraction. So we assigned the background a default 95% of the TDI and allow you, when you're doing your screening, only 5%. So the MDES portion ends up being only 0.015 microgram per kilogram per day, per kilogram body weight per day. For cadmium, JECFA has set a provisional tolerable weekly intake of 5.8 microgram per kilogram body weight per day, which you divide that by 7 is about 0.83 microgram per kilogram body weight per day. To estimate how much we could be getting from background, we looked at the total diet study. You just heard about the total diet study a minute ago. We used data from the total diet study from 2001 to 2006 and estimated that from the diet we get about 0.19 to 0.36. The mean was 0.19, the 90th percentile was 0.36 microgram per kilogram body weight per day. And using also the limit on water of 5 microgram per liter that FDA has set, we estimated the potential exposure from water, assuming 2 liters of water per day, of 0.17 microgram per kilogram body weight per day. So that would be what's in the background. When we add these together, this leaves us, and subtract that from the 0.83, that leaves us a range of 0.3 to 0.47 microgram per kilogram body weight to use in the MDEST. Chromium, we need to worry about 2 chromiums. We need to talk about 2 chromiums, chromium 3 and chromium 6. Chromium 3 is a lot less toxic, and basically, while chromium 6 is a carcinogen, and therefore the limits will be very different for the 2 chromiums. So depending on the type of chromium that is found in the product, you need to use one or the other of those values in the MDEST. And again, the MDEST walks you through this. For chromium 3, there is a limit set by EFSA on supplement of 250 microgram per day. So we said if that's our upper limit, what could be taken out by the background, by the available exposure, already existing exposure. The Institute of Medicine evaluated the exposure to chromium 3 for different subpopulation, and the range was from 15 to 54 microgram per day. And then the ATSCR, the Agency for Toxic Substance Disease Registry, has also estimated the exposure from drinking water to 7.2 microgram per day. So using these two together, subtracting them from the 250 microgram per day, we estimate that the MDEST portion you could not exceed the 188.8 microgram per day. For chromium 6, EPA has set a reference dose of 0.9 microgram per kilogram body weight per day, and in that particular case, we used the same approach we used for arsenic and said 95% of that would be for the background, the remaining 5% or only 0.045 would be allowed in the MDEST. All of these are 2 values that you can go in and update if new data have become available. So because, as I mentioned, agencies are still updating their, you can always see new numbers coming out, and so you could go in and change these numbers in your model. Lead. FDA has set a provisional total tolerable intake of lead for different age groups because lead is a reproductive toxicant, then different levels were set for different age groups. So the most sensitive subpopulations would be children and women of childbearing ages. They were given the lowest PTTIs. You see that the youngest children has 6 microgram per day. Women of childbearing ages, pregnant or lactating, get 25 microgram per day, while other adults would get to 75 microgram per day. The way we approached lead in the MDEST, we basically decided, again, it's a bit arbitrary, but again, this can be modified by the user, that children and females of childbearing ages, the most sensitive vulnerable subpopulation, we assumed that 50% of that PTTI is already taken by the background. So we've only allowed 50% of that to be used in the MDEST. For the other adult, we assume that 1/3 of that PTTI, the 75, is through the background, and therefore allowed 2/3 of it, or 50 micrograms, to be used in the MDEST. And I think mercury is our last one. Mercury, JECFA has set a provisional tolerable weekly intake, a PTWI, of 4 micrograms per kilogram body weight per day, which is equivalent per week, sorry, which is equivalent to 0.57 micrograms per kilogram body weight per day. We used data from the FDA Total Diet Study and estimated a mean of 0.06 at a microgram per day, kilogram body weight per day, and a 90th percentile of about 0.14. And then using also the bottled water limit that FDA has set for drinking water, we estimated the drinking water to be about 0.067 microgram per kilogram body weight per day, which leaves us for the MDEST range of 0.36 to 0.44. So now we've set that first part, which is what is the maximum limits that are allowed in the MDEST. So that was our hazard characterization. Now we go to our dietary exposure section. For the dietary exposure, we need to combine our concentration, how much we find in food, with the consumption data, with how much we eat, because basically that's what dietary exposure. To do this, we have set up different options for users depending on the type of product in which the compound has been found. Our first, most broad category is using the CFR categories. When you take a can of or a bottle of water or anything, you have those default serving sizes that are on the label. So basically, if you go to 21 CFR, when you go through a list, you can see all those various categories. This is where most of these serving sizes come from. So we use there are 45 categories that are set in the 21 CFR. But again, these are pretty broad, and I'm going to give you examples next to see how broad these levels are. When we looked at these, we thought, well, sometimes your product is not found in baked good, it's found in a bagel. That's what you need to worry about. You don't worry about everything, or you don't make everything, you make bagels only. Then we expanded those 45 categories to 320 categories, and I'll give you some examples in a minute. But also your compound could be found in raw agricultural commodity. It could be found in rice, could be found in sugar. So basically you're not talking about a finished product, but you're talking about a raw agricultural commodity. So also we give you data, consumption, pre-calculated, pre-populated data of how much people eat of various raw agricultural commodity, RACs. You heard about the Total Diet Study. We also use data from for the various, I think the Total Diet Study includes about 286 food groups. So we used consumption data for those 286 food groups and present these to you. And then finally, because we were interested also in looking at infants and toddlers' diets, we looked at summary data from the Feeding Infants and Toddlers Study, FITS for short. We did not have access to the raw data from this survey, from this study. However, we had access to summary data as published by EPA Exposure Factor Handbook. So we used the consumption data from the published summaries there. I mentioned the data so these are the broad categories, and then we went to the raw data from NHANES or from the precursor of NHANES, which used to be called the CSFII, the Continuing Survey of Food Intakes by Individual, and compiled consumption data to use for those various for those various categories. The reason why we use different databases is because at the time, whatever was available to us was NHANES 2005-10. This was the most recent. So we used that for the first two categories, for the CFR. To go to the raw agricultural commodities, we needed to take the food as consumed by people and break that into raw agricultural commodities, into those find recipes. And EPA, at the time when we were developing the tool, had only recipes available for the NHANES 2003 to 2006. That's where the FCID comes from. It's Food Commodity Intake Database, for those of you who don't like acronyms. This is why we stopped at 2003, 2006 for the FCID. For the total diet study, whatever was publicly available to us in terms of amounts consumed of the food groups, the various food groups for the total diet study, was from that older survey, the CSFI 94-96. I understand that FDA is updating and will be putting out their consumption data based on the more recent data for their food groups. And I mentioned FITS a second ago. I'm not going to go there. Just to give you an example of what these types of food look like. So the first category, the broad CFR category, you see a category called baked goods and baking mixes. Everything that could be baked good fits in there, or all breakfast cereal, whether they are ready to eat, instant, hot, etc., would be under one group. So if you really want to be very conservative, you probably would go that way and use a very broad levels, those very broad categories. Alternatively, if you want to refine it more, you can go to what we call the refined category. And here I'm showing only a fraction of anything that fits under the baked good. So we took that baked good and broke it down into all these categories and provide in the tool consumption estimates for these various food categories. For the FCID RAC categories, it's about 300, I think there are probably about 350 or so different tracks in the FCID database. We compiled these a little bit, and here again, this is only a sampling of the type of agricultural commodities for which we've provided consumption data for. The total diet study, again, I just picked the top of the list, and you see here about 10 or 15 of those types of foods that are in the total diet study. Again, you can, I guess I'll give you in the end the website from where you can go and download that, download the tool and look at the entire list of categories. For the FITS category, for the FITS study, the toddler and infant studies, again, only a sampling of the types of foods for which we've provided consumption levels. So the tool includes these we talked first earlier about all the stocks data or the risk characterization data that you could change yourself, that you could put in, update with new data. Here, the consumption data that's used in the dietary exposure is hardwired. You cannot really change those values. We provide these values for 5 population subgroups generally, the US population, infants, 6 months to 2 years, children 2 to 6 years, children 7 to 12, and then female of childbearing ages. That's when we're dealing with the CFR categories or the FCID categories. When we went to the TDS, because we're using whatever FDA has derived and put out there, we had to use the data, the age groups that they provided, which are total US, infants 6 to 11, children 6, children 10 to years, and females 25-30. So more or less the same age groups, but whatever is out there is available. And FITS, again, because it focuses on infants, it's a different age group that we've provided you. So the tool comes in pre-populated with per capita two-day average consumption values and a % consumer for all those food groups that we mentioned earlier. And so that's the consumption data. Now we know about consumption. What's exposure? Exposure, as I said, is how much you eat and how much is on that food that you're eating. So basically, the way the tool works is you put in your value for how much is found on the product, and then it calculates the exposure for that particular food. If there are multiple foods that are affected, it calculates a per capita mean by simply summing over the various food for which you've plopped in a value. That's very simple. For a per user, if you're only worried about consumers of given foods, because we know we've provided in the tool the % consumers, it basically takes the per capita mean divided by % consumers, and that gives you the level, the consumption, the average consumption level for a consumer. If we have more than one food or food group, then we estimate the percent consumer by assuming complete overlap between the two. Remember, what's in the tool is already pre-processed. So basically, we have those summary numbers that we need to use to come up with a global total intake. And because of that, we have to make some assumptions. So the most conservative assumption would be to assume a complete overlap because that gives us the smallest percent user. And by having the smallest percent user, that means the per user number will be the highest because that's in the denominator, as I described a little bit earlier. So that would give us the per capita means per user mean. How do we get at the 90th percentile and other upper percentiles? We use FDA's pseudo upper percentile approach, which basically says the 90th percentile is about 2 times the mean. The 95th is about 4 times the mean. The last one, the 99th percentile, was our own extension. We basically said the 99th percentile is about 6 times the mean. It's pretty conservative, but we put it in there. And again, we remember this is a screening tool. This isn't an actual dietary exposure tool to evaluate exactly how much people are exposed to. I'm going to be presenting very briefly a few screenshots, but I think Dr. Lee will be demoing the tool, and there you see more detail on that. So when you go in to try to put in the concentration after you choose the type of food you're working, the type of database you want to work with, and you want to pull in the concentration data, you are also allowed to say, well, actually, it's not, here the example isn't really a very good example. I have apple juice, but I have percent juice, but say you said it's a pie, and the contaminant is not found in the entire pie. It's not found in the entire pie, but it's found only in apple. Then you could go in and say whether it is found in an ingredient in that particular food. And if you have that information about what fraction of that food that ingredient is, you can add that fraction in here. For arsenic, we've been talking about arsenic in general, but the tool assumes that the exposure is for inorganic arsenic. So, because that's the more toxic form of arsenic. So if your data, the concentration data that you have, are for total arsenic, and we are using the values for inorganic arsenic, there is a disconnect there. So the tool allows you to go in and say, well, actually, my data are for total arsenic, but I can convert my total arsenic value to inorganic by putting some sort of rough ratio that you could put in, and then, therefore, it allows you to use that ratio. We're calling it a conversion factor. So we've calculated our exposure. What does that exposure mean? Again, I keep reminding you this is a screening tool. So the first way we evaluate our exposure is simply by taking our exposure estimate and dividing it by that fraction of the NDES that we've allowed you. So we come back and say, okay, the exposure is 50 microgram per kilogram per day. You're only allowed 100 microgram per kilogram per day. So you are at about 50% of the allowable exposure. Or you estimate it to be 50, your allowable is 25, you're at 200% of the limit. So basically, it gives you that fraction of the allowable tool. The other way it characterizes risk is by saying how many servings of food can you eat before you exceed the limit. And so it provides you that way to look at your risk, to estimate your risk. We have two approaches also when we develop this model. Is one of them would be to say, well, the entire exposure comes from a single food, or if you know you have multiple foods, we allocate the exposure over the various foods, and then it comes back and tells you how many servings of each of these foods you would be allowed to have before you exceed. The serving sizes are serving sizes that we put in based on the levels that the serving sizes, the default serving sizes in the CFR, the RAC serving sizes, which stand for, reference amount customarily consumed. But if your product has different serving sizes, you can change those actually in the tool. Just final 2 slides. Remember, this is a screening tool, and I'm starting always with that. Remember, it's a screening tool. It tends to do, it is designed to be very, very conservative. That's on the one side. For some contaminants like cadmium and mercury, we have a really large fraction of the PTDI that's available for us to use in the tool. We have to be very careful not to use that entire thing for one incident. I mean, finding a lot of cadmium or a lot of mercury in a particular product and then assuming it is okay to have that just because it passes doesn't mean it is safe. We have to go back and make sure that we don't use that entire fraction. And finally, if there are limits that have been set by other agencies, you should take that into consideration and not say, oh, I'm fine, I don't exceed. But if your values exceed those limits, you should not be really accepting them. And as I mentioned, the tool is available on ILSI's website, free to download by everybody. Even we have a manuscript and risk analysis that describes it with a little bit more detail, so you have access to that. And there were a couple case studies that are available. Questions? But I think I took a lot more time than I was supposed to. Sorry.
Any questions?
Very nice presentation, thank you. So for metals in particular, there are many other sources of exposure that have been identified, like household dust, personal care products, cosmetics, environmental exposure, and so on. I'm just wondering, did you consider that at all when you were setting up your background exposure? Because you only seem to apportion it to the food and diet.
Yep. We only considered food and water. But as we said, these levels, you are allowed to, you're allowed to I'm losing my voice, to change those values. You know, you can go in and change these values. But you also have to think where those limits come from. I mean, those exposure values or limits that we are using are for dietary exposures. So you'll also have to think what the limit would be for the total exposure if there are those limits. So that's something to take into consideration.
Just an interesting follow-up from a European perspective at the moment. The European Food Safety Authority, on the one hand, are requiring aggregate exposure assessments to include all sources now.
Mm-hmm. Yep.
So that's a kind of there's a regulatory drive
Yep.
there as well.
Yep.
Equally, on the cosmetic side, there's the Scientific Committee for Consumer Safety, and they're for CMR substances in particular, they're requiring all sources of exposure to be included in your assessment. So it's just heads up.
Again, yeah, and actually EPA has their own model, the CalIndex model that they use, that also looked at dietary as well as residential exposures. So you're absolutely right. I mean, this is why you're allowed to change those values yourself.
Thank you for the presentation. It's been excellent so far. I apologize for my ignorance, but I'm more in microbiology, so this is kind of new to me, so that's why I wanted to be here. Looking at the toxicology of the metal, is there studies done on how much the body actually extracts from the food when consumed? And is that considered in the toxicology assumptions that, yes, it is going to be harmful at that level, but is the body totally taking it all in, especially looking back at your study that you're talking about? The kidneys were full of the metals, but the meat was not.
Yeah.
Yeah, distribute. Yeah.
Yeah. Those reference doses or limits that were set do take the absorption into consideration. Whatever, you know, the limits that are set by the regulatory agencies that we have used. We did not then take the diet itself and then adjust it for absorption. We did not do that, basically. In our model, we don't adjust. We don't say, okay, if that's how much is found in rice, then, and you can only absorb that much when you eat because the rest of it is going to go, is a pass-through. Our model does not do this pass-through, does not adjust for this pass-through. But this is something, because if you know that, then you could adjust the concentration value that you put in by that pass-through if you needed to do that.
Are there studies out there on the pass-through?
I'm not a toxicologist, but there probably are. I'm sure there are studies out there on that, yes. And if there's somebody in the audience who can help with that?
So that's a great question. You know, as Layla was talking about, this is a tool of a part of a holistic risk assessment that we put together. So bioavailability of metals, the absorption of metals, these things have to go into the risk assessment if you're dealing with a particular situation where you have higher than normal levels. So for instance, and then there's also a lot of knowledge. So for instance, arsenic, selenium acts as a natural antagonist against arsenic. There's been studies in pigs where arsenic in the context of a food matrix is only 40% bioavailable, and some have differences depending on species. So you have to look at all of these things along with the tool and to do the risk assessment. And at General Mills, we have, you know, this is based largely off of publicly available databases, but for instance, we have databases internally. We know how many kids are eating Cocoa Puffs on a daily basis. So, you know, we get really specific to our products to where we may find heavy metals or not. But, you know, as the gentleman before you was saying, this is becoming a global issue. You know, a lot of people will say, well, heavy metals are in the Earth's crust. It's been around for ages and ages and ages since the beginning of time. True, but analytical chemists aren't helping us all either, you know. So I'll give a specific instance since we have time. About 4 years ago, an activist organization found parts per trillion levels of mercury in our yogurt, and we own Yoplait. I believe the level is 32 parts per trillion. Well, you look at the risk assessment and you base it on EPA standards, et cetera. A 20-pound child could eat 5 times his or her weight in yogurt before getting to the safe level. But the consumers, all they see is 32 mercury yogurt. Parts per trillion doesn't mean anything. So back to Dr. Ortiz's slide, you know, it's all about dose makes a poison. But this is something we have to contend with. Whether it be academia, regulatory agencies, or industry itself, we have to be able to translate these messages, and we're finding these all over. I mean, based on the first presentation, metals are everywhere. Can't get away from them. So, yeah, your point is really well taken. Great question. You know, no two metals are created equal from a toxicological standpoint. So, but yeah, are there any other? Does that answer your question?
Yes, sir.
Okay, great.
Yeah, I come from industry, and I have kind of a similar question. There's a federal EPA limit on hexavalent chromium for somewhere in the vicinity, 100 ppb, and the state of California obviously has lowered their maximum contaminant level to 10. Can you just speak about the risk assessment that's involved from a state level versus federal, and how California may have come to a conclusion that's different? I know it's an ongoing study, but I'm just curious.
Yeah. Oh man, we could spend an hour on risk assessments and what regulatory authorities come up with their risk assessments. I believe in California, correct me if I'm wrong, please, because I'm trying to keep these all straight in my head. Prop 65 will take a 10,000-fold, I'm sorry? Yeah, safety factor when determining. Others will take 100-fold safety factors, 1,000-fold safety factors. I mean, it just depends on the regulatory agency and what they view as safe. Going from, and that's where, you know, you always have to balance risk in my mind. You know, first and foremost is food safety risk, safety of the consumer, et cetera. And then you have to balance, and once you check mark that box and look, this product's safe, we have no doubt in our mind, what is the regulatory risk? Where are we selling this product? Are we selling it in California? Are we selling it all over the US? Are we selling it just in Europe? Is this Australia, New Zealand, et cetera? I mean, I'm giving a talk on allergens later this afternoon, and even there, regulatory agencies differ in what they view as priority allergens. So 10,000-fold safety factor, personally, as a toxicologist, I think that's way too much to extrapolate from species to species variation and then interspecies variation. I tend to stick with the 100-fold safety factors when you're doing that, but Prop 65 and OEHA out in California has taken a very conservative approach to what they list. So it's a matter of regulatory risk as long as you have the food safety risk all ironed out. And a lot of that is how your company views regulatory risk and your interpretation of the different laws from state to state, country to country, et cetera.
The difference is driven by Prop 65 in this case.
In Chrome 6, I'm not quite sure. I can't answer specifically on that. I apologize for that. But a lot of what is driven on the chemical and what is deemed to be labeled or known to the state of California to cause cancer or regulatory harm is driven by OEHA and Prop 65. So the Office of Environmental Health Hazard and Assessment. So, yeah, I would have to look into that specifically to answer your question, so I can't answer right off the top of my head.
Thank you
All right.
for fielding this.
Yeah, thank you. I'm sorry I couldn't answer that specifically, but, yeah, it's something to check out.